On that quick guide to the experimental procedure, and really, if there's anything at all that y'all want to go through tonight or tomorrow, I mean, even if you just want to text me a question on Remind, please just do that anytime you feel like it. If you're working through these review problems and get stuck or have a question, let me know. Hey, did either one of y'all add the Twitter, the AP Chem tip line thing?
No, I don't actually have a Twitter, so I couldn't.
Oh, that's too bad.
Yeah.
So I may like post all those over to where you can see them somewhere.
I will definitely look at them if I can, or I can actually probably just.
You can probably look without even having an account.
Yeah, I think I can. I'm gonna see if I can.
But he started that today, so if you're following him. It's a thing. This is an older AP Chem teacher. He's really awesome, and he's done it in the past as a Remind group that kids all over the country have added. But this year Remind cut off their like enrollments at 150, so you can't.
Oh yeah.
So he couldn't do that. They wouldn't let him do that. There it is, Jean Lynn AP Chem tip line. All right, so let me show you. It's just like super useful stuff. I'm going to screen share with y'all for a second.
All right.
Y'all, I'm out here with the dogs. It's always chaos, no matter where I go. Dub, hush. My bulldog, if anything makes a bumping sound at all, he just goes crazy.
That's kind of like my dog. Like he can hear like a knock on a table or something. He just barks the entire night.
I mean, my dog is like half deaf, but it has to make like a thump or something, and then he just goes berserk.
Oh, so you have a little bit of leeway.
Oh yeah, it has to be a good. Okay, so can y'all see this?
Yeah, I can see it.
Hang on, wrong. Let's switch back. Dang it, I keep clicking on the one behind it. There we go. All right, Jean Lynn's AP Chem tip line. So just reading through it, some of these, he sends them out he has them set to go out every 5 minutes. And they're just little, I love it when it was on Remind because it just popped onto your phone every couple of minutes, the 24 hours leading up to the exam. Some cool thing to remember. So like here we got silica and silicon dioxide are giant molecular structures similar to carbon. And you know that, like we worked one problem that had silicon as a covalent molecular solid, kind of like graphite, like carbon does. It's in the same family as carbon, and it's one element underneath carbon, but it's just a good reminder. Like it is not a standalone element. It's like carbon. It makes these big molecules, these big molecular structures. The electronegativity of your elements. You guys, I mean, I doubt that you need to know the trend and you need to be able to explain the trend. That's the unit 3, Coulombic attraction and shielding and effective nuclear charge. The higher electronegative, fluorine is the highest, right? Knowing the trend doesn't help you answer any questions. You have to be able to explain the trend. But it's good to know. You need to know the trend so you don't have to think about it too hard of what's the most electronegative. Volumetric flasks do not need to be rinsed. Add your chemical and fill to the line. Yep. Proper way to use a burette is rinse it first with your solution. You don't rinse it with water. You rinse it with what you're going to use. When explaining lab-based errors, now he is strongly of the opinion that there's going to be lab-based questions on here. But if it's anything like the AP exams that have happened so far this week, every one of y'all will probably get a different exam. That's what I think.
Yeah, that's probably
looking at the lit prompts today. No two people that I talked to had the same passage to write from.
Oh, really?
Yeah. So
there's probably a lot of different tests then, like tons.
Yeah, that's what I'm thinking, that they're gonna. It might even be to where we split up so much to where like each little small group of readers just does one test. usually they split us up by question, and I'll read like question. There's 7 for your response. I'll read question 2 all week long, and I always get
Oh,
on question 2. I'm guessing we may do question 1 and 2 of like we may do one whole test because it's a shorter test
right.
and grade both questions for one version of the test. I don't know. I don't know what'll happen. So y'all's what I end up grading might not even be anything that you guys answer. And I suspect they're being super intentional about kids that know each other. So like kids that are at the same school um, probably won't get the same test.
Dang.
What was that, Hayden?
I said, dang, that's crazy.
It is kind of crazy. I know. Yeah, I know there were a ton of versions of this literary analysis passage today for AP Lit. So I don't know how many versions we'll have. So some more little reminders. Hydrogen bonding is intermolecular, not intramolecular. So between 2 different molecules. And it's not a real bond, but it's a force. Rate constant, little k, has units, but big K, equilibrium constant, does not have units. Changing phases involves breaking intermolecular forces, not bonds. So many, I mean, look how many good things are in here. It's just like little chem facts that are helpful to remember.
How long has that been going on? That's a lot of tweets.
He started it today. He started at 3:00 this afternoon.
Wow.
But it goes
Goodness.
out every 5 minutes.
Oh, I guess that's true. That's true.
They're just like little nuggets of chemistry wisdom.
I'm gonna like have that page open during the test just so I
You
can look at everything.
can, and you can also search it. But I can also paste these over into our shared drive in a file. Oh, here's the other thing about the shared drive. All right, so let me show y'all how to get to the shared drive. If you go to your teacher's websites, which y'all are all familiar with, I'm sure, you find me, and then scroll down to AP Chemistry. And if you click on just the word AP Chemistry, it'll take you there, or you can go down further where it says AP Chem Files. But that'll just take you to a Google Drive that has only AP Chem stuff. And look, they're not sorted. I'll probably go through and organize these and put all the cheat sheets together. Because like, I don't even know what kind of order it just put them in. Oh, it put them in by date they were created. Like I just put all these cheat sheets in there, but they're by the date that they were created.
Oh.
So anyway, I'll organize those after we get off of here. But they're all in here. I'll make another one with the little AP Chem tips. But you cannot access a shared drive during the exam. You're not supposed to. If more than one because people could be meeting up on a shared document and cheating. But you can steal any of these. You can like click on, if you want Hayden's Unit 5 cheat sheet, just click on it and then make a copy. And it'll make a copy into your Google Drive.
Oh.
I won't let me, where can I make a, so like under file, you can go to make a copy and it'll add it to yours. I don't even think you have to open it. I think you can just do it from, you do it from like a control. Yeah, if you just hit the control file name and then hit make a copy, it'll make a copy in your Google Drive.
So do you think they're going to be like filming it, like, or like watching us?
I don't think they're going to be watching, but I think they're going to be watching things like internet traffic and people that are accessing shared resources, like the shared Google Drives and things like that. Like if all of y'all got onto a shared Google Drive page and started chatting, they would investigate that. They would check and see if people were cheating. What they've said is that they're going to take anybody that they know is cheating. They're going to take that knowledge and share it with all the colleges that you've applied to. So that's ugly. You don't want that.
Yeah.
Nobody wants that.
Not really.
But like if I looked up like if I saw something and I was like I wanted to look up like a constant or like if I wanted to look up like what oxidation was, would that be like?
Oh yeah, that's totally fine. Like you're allowed to Google anything.
It's so weird how all this is working out. Like we're allowed to use the internet for our tests.
You're
Since when?
just, well, for, strange circumstances, you're allowed to use any resources at all except except other people. Right? You can use your books, you can have notes, books, reference pages, internet, you can have all those things spread around you while you work on this. But the truth is the timer is ticking and it's ticking fast.
Yeah.
And it's better to just plow straight. What I would do is plow straight through the question and answer as much as you can first and see where you are on the timer. Like answer as many things as you can and have that stuff saved and ready to go. And then start if you need to consult your outside resource. If you still have time left and parts left, then start using your other resources. Definitely if it's something that you have somewhere on a sheet, like if you know for sure that you have a great explanation of that, dig it up and read through it. Make sure you don't make a careless mistake in that. All right, so let's run through this quick guide to experimental procedures. So this first one, gravimetric analysis, this is one of our labs. Now we've worked some problems that have gravimetric analysis, like where you get the mass of a product and kind of work backwards to figure out using the stoichiometry and work backwards to figure out what was there, like how many moles or how many grams or whatever, or how much calcium is present or just whatever. But gravimetric really means filtering and weighing. So anytime if you see, it's like you're doing it by gravity and we use gravity filtration. And this is one of the labs that we were supposed to do after spring break. And we've done the math. We just haven't done the actual experiment. But so these are the big overall steps. You make a precipitate. So you'll mix together two things that are soluble, but when they combine together, they form an insoluble precipitate. And then you would collect that precipitate on a filter with a piece of filter paper and then rinse it to make sure that everything else is gone, and then dry it and get the mass. And you would usually we'll dry it and get the mass 2 or 3 times or until the mass is stable. It says until a constant mass is obtained. If you dry it and weigh it the first time and then you dry it and weigh it the second time, almost always it's going to be a little bit less mass the second time. Why? Like, why does the mass keep dropping?
Because more of it's reacting.
And really at the end, it's done reacting. It's really just not all the way dry the first time.
Oh, that's true.
It really takes a couple of drying attempts to get it dry. And so that's under our common mistakes. It might not be all the way dry. And if, like they could say, what would happen if the precipitate was not all the way dry, or if you only dried it one time? And then you would want an answer kind of like this. Your percent yield would seem to be higher than it really is. You'd really be weighing your product plus a little bit of water, right? Some of that mass would be from water. Use this a lot to figure out like one particular ion in a solution. And they're pretty much always going to ask you for the net ionic equation on those. And the net ionic equation is whichever ions come together to form the solid. And so we don't include the ones that are soluble. You wouldn't include any of your spectator ions. So no sodium, no nitrate, like basically no group 1 metals and no nitrates, no ammonium, because those things stay soluble. All right, the second one is where your picture didn't copy very well. The making solutions. We did make some solutions on the day that we did the Beers Law lab, the dissolving the copper and dissolving the brass bullet and figuring out the copper. and we made solutions on another day, but you have to use a volumetric flask, and the volumetric flask has the long skinny neck and the etched glass line. And if you forget what any of them are called, on the very back of that packet is the picture of all the glassware. Y'all see that? Except our volumetric flask is not on that picture, is it? I'm gonna draw him in there. I picked, this is the one, yeah, that I had saved, but we need our volumetric. So for making solutions, you got to use a volumetric flask because that one is designed to contain an exact amount of liquid when you fill it to that etched glass line. And so we'll dissolve, you would put it in there, dissolve it, swirl it around, and then carefully fill it to the mark. Fill it up to the etched glass line where the meniscus of your water touches the etched glass line. Any questions about that?
Sounds good.
Got to know about molarity is moles per liter. You can make a known volume of anything. Yeah. Got to try to remember to use distilled water and be careful about not going past that line. All right. Oh, all right. The third one is titration. And we've got, here's the, oh, did y'all do titrations? Where you turn it light?
No, I don't know.
I don't think we did.
I don't think we did either. I can remember y'all doing them, but really that's last semester. So you add your, this is just really, it's almost always a neutralization reaction where you have an unknown molarity of acid in a flask, and you're going to fill a burette with a base and then add it dropwise until it gets to the neutral point. And so you can't see really well on that picture, but this is a color change happens right here. Right, when you get to the end point of the titration, you use an acid-base indicator that changes color at the pH of the end point. So some of this stuff we can ignore, like this the pH at the equivalence point should be equal to the pKa of the acid. Y'all remember they cut out 2 units that we didn't end up having to learn? And all the stuff about pH and pKa, almost all of the stuff about acid and base chemistry was in that. But titration I still included it here because they talk about it just a little bit in Unit 4 in the reaction, because it is a neutralization reaction between acid and a base. And titration just means like slowly, if you titrate anything, you're slowly adding one of the reactants just dropwise to like make a carefully controlled reaction. Does that make sense?
Yeah.
So titration ends when you have the exact stoichiometric amount that you needed. So if I had 1 mole of hydrochloric acid, then I need 1 mole of sodium hydroxide to neutralize that. So you would just keep adding drops until you got to exactly 1 mole. And so some of the words for titration, your analyte is the thing that's down in the flask that you're titrating into. And in your burette is your titrant. And standard solution is anything that you absolutely do know the concentration of. Okay. The next one is Beer's law. And that is where we use the spectrophotometers to figure out the percent copper in brass. And so how the spectrophotometer works is you have the light source that gets separated out into its wavelengths, and then we select a wavelength. Do you remember how we selected a wavelength? We put it up on the screen and we looked at that copper solution was like blue, very blue. And so we ended up selecting a wavelength that was like in the reddish orange region.
It's the color that it absorbs the most.
Yes, the color that it absorbs the most. And so I can't remember what the exact wavelength was, but we just looked at it and picked a wavelength where the absorbance was really high. It's like for the one that's shown here in this graph, 280 would be a good wavelength to pick, right? For whatever that is. And that's in nanometers. And so then that single wavelength of light went through our little blue sample and straight to the detector, and it measures how much light passes through and how much light gets absorbed. And we can choose whether we want to plot absorbance or transmittance. Those are the opposite of each other. And then we made a plot just like this, instead of cobalt, ours was copper, but the molarity or molar concentration of copper versus the absorbance. And we made a standard, like we did it at these exact, did we do these? I think we did these exact concentrations. We did at 0.02, 0.04, 0.06, 0.08, and 0.1 molar, and then got our line of best fit. And then you guys took your bullet casings and diluted it down into a range that would be in there and measured its absorbance. And we worked backwards. Like we got from the absorbance, like if the absorbance of your bullet was 0.4, then we would read that off of this graph to be about what? Maybe like right in here? Like a little above 0.7, 0.72, 0.73, something like, 0.072. Y'all see that?
Yeah.
So once you know what the absorbance is for your unknown, you figure out the concentration from that. All right, so this is actually Beer's law, this weird little equation where absorbance is equal to molar absorptivity times the path length of the cuvette times molarity. And we don't worry about these. This molar absorptivity is different for every material. And then the path length is always 1 centimeter. And so we just say absorbance and concentration are directly proportional for colored compounds. Beer's law does not work for colorless compounds because these are, if it's colored, then the more concentrated it is, the darker the color is. And the more dilute it is, the lighter the color is. All right, so if you have a question about Beer's law, you can look back at the common errors here, common mistakes. If the cuvette was dirty, if you didn't wipe it, or anything else like that. All right, chromatography. Chromatography, everybody should have done in first year chemistry, and then we set up one that looked kind of like this as a demonstration where you use basically a special kind of filter paper called chromatography paper to separate out the different pigments that something is made up of. And we use a solvent that the pigments are slightly soluble in, so then their polarity of the pigments is what causes them to separate out. And then there's a little review of how to tell if your compound is polar or nonpolar. So your nonpolar substances are going to be most soluble in nonpolar solvents. Polar substances are more soluble in polar solvents. And you can separate, it's a separation technique. It's also a purification technique. Y'all see this little chromatography paper here with these spots on them where they're all different? You can literally take your scissors and cut out one of those spots and literally get a pure form of that compound, whatever it is. Like you've separated it out of a mixture and you have pure whatever that compound is. Like if you're separating food dyes, you can get a pure sample of red number 40. And so it's pretty cool. The first time I did that was in graduate school, and I did it on a large scale, and I was pretty impressed with it. I thought it was pretty awesome that you could take something and separate it out by literally cutting it out of the paper. All right. Next one, fractional distillation. Y'all remember the day we got to observe Boswell doing this for us?
Yeah, I do remember that.
He had just ordered a condenser. And so fractional distillation is another separation technique that lets you separate things by their boiling point. So you heat, when you heat it and boil it, you're breaking the intermolecular forces, you're moving those molecules into the gas phase, and then the condenser is colder. It has cold water running through it, and so the gas phase molecules literally condense and then drip down into your collection flask. And it'll hold steady at a temperature, and you can collect all of whatever is coming off at a certain temperature. And then when the temperature starts to rise, you change your receiving flask. And so you can separate out like all kinds of stuff. We've done essential oils out of crushed flowers, which is kind of cool. But you can separate compounds that way by their boiling points. So the thing with the lowest boiling point is the first one to come out, has the greatest vapor pressure and the weakest intermolecular forces, and that's back to unit 3 again, right? The higher the boiling point, the stronger the intermolecular forces. All right, the next one is calorimetry. Coffee cup calorimetry, styrofoam cup calorimetry. We did calorimetry 3 different ways. The Q equals MC delta T stuff. While you guys burned the foods to figure out the calorie content of the nuts. And we did the heat lost by the nuts was equal to the heat gained by the water. And so we did the Q equals MC delta T for the water as it raised temperature. Well, this one is the one that Ari and I were working on in the back. Like if you drop a piece of warm metal in here and measure the temperature change of the water, you can calculate the C for the metal, the heat capacity of the metal, or you could mix together 2 liquids that react and calculate the heat of that reaction. So like if we mix an acid and a base, it gives off heat. We can Q equals MC delta T that. Common mistakes, not stirring, not having a valid representation of the temperature. Final temperature is highest for exothermic. Yeah, your delta T needs to be your final minus your initial temperature, even if the final temperature is not the highest. And this is super important. Don't mix these up. I'm sure there'll be at least a tiny bit about this. That endothermic, they get colder. They're pulling energy in from the surroundings to make that reaction go. Oh, we have more participants. Ari's here.
Hello.
Hey, Ari.
Hey, Ari.
How are y'all? Great. We've been running through this lab packet, and we're talking about, well, we're getting close to the end of it. We're on the calorimetry. And talking about some things to remember.
Sorry, I was a bit late. We eat dinner a little late over here.
Sure, no problem. Okay, so your endothermic always get colder. They always have a decrease in temperature because to make that reaction work, they're pulling heat in from the surroundings. So when let me show y'all. Y'all remember keep these energy diagrams in your mind too. Reactants. Whew, a bug just got on me. Can y'all see that? So like endothermic, your products end at a higher energy than the reactants, right? Energy overall went into the system. For exothermic, they always get hotter. They are releasing energy to the surroundings. And so that energy diagram is flipped where your products are going to be lower than your reactants. Your Q equals MC delta T. Keep all that stuff straight. Pay attention to the units. Here, the temperature doesn't matter if Celsius for temperature, grams for your mass, joules for your energy. And then your delta T is final minus initial, even if your final is colder. It's just going to give you a negative delta T if it's colder. And what would it mean about it? It means that it's endothermic. Endothermic. Like heat had to go into it, which kind of sounds backwards, but it made heat go away from the part that you touch, away from the surrounding. And so the surroundings get colder. All right, this one, I know the picture didn't show up very well on this either. Y'all see it? Preparing solutions by dilution. So after we made our initial solution on the Beers Law lab, we made dilutions too, where you take out stock solution is just the one that you know the concentration of. Your dilution is what you're making. So if I have a 10 molar, if I have 1 liter of a 10 molar solution, and I only need I don't need a 10 molar solution, I only need a 1 molar solution. How am I going to make a 1 molar solution from a 10 molar solution? That's the kind of question that they might ask you. And that's where this M1, I think I added it to y'all. So I put M1, oh, there it is, M1 V1. I think I typed it in the notes too. M1 V1 equals M2 V2, where your molarity.
Yeah, I see that on the, it's on the paper, yeah.
So that's just a reminder that the moles that you pull out of your concentrated solution are going to be the same moles that are in your diluted solution. They're just spread out with more water. So like molarity times volume is moles. But so like M1 V1, that could be our concentrated solution. Let me show you a quick sample problem with that because I feel like I'm saying too many words. Let me switch. Can I switch? Camera. I'll just pull it up on a document. No. All right, so the kind of question you might see would be something like this. How many milliliters of 10 molar solution are needed to form 1 liter of a 1 molar solution? Doesn't matter what it's made of or anything else. All we're doing is we're going to dilute this. So y'all know how to do this? So this right here is I would call this my M1, my concentrated molarity. How many milliliters? Well, I don't know how many milliliters. That's what I'm looking for. So my V1 is question mark. I want to make a liter of my dilute solution, so that's my V2. And I want it to be 1 molar, so that's going to be my M2. And so it will look like this. 10 molar times, I don't know how much of that, times V1 equals 1 molar times 1 liter. And it doesn't matter if you use milliliters or liters in these, as long as you keep them the same on both sides of this equation. So I picked this because I can do this without a calculator. Actually, I've heard in the physics test, they really didn't need calculators. And they implied in those review sessions that you really might not need calculators on our test tomorrow. I think there's math, but it's just not going to be calculated.
So it'll be like easy to do with your head type thing.
I think so, kind of like this, right? So my V1 is going to be 1 divided by 10, or 0.1 liters. You'll see that? So a second part of this question could be describe the preparation of that solution. And so you would have to say, you would take, so look back at your solution preparation one that we just skipped over. I mean, we did it, but it was early on. Making a solution. Number 2, you're going to take out 0.1 liters of stock solution from the 10 molar, well, How about that? 0.1 liter of the 10 molar stock solution using a pipette. Transfer it to a 1 liter volumetric flask. And what? Dilute it to the mark. Etched glass mark with distilled water. And that's it. So if you have to describe the preparation, you want to say how much and what equipment that you're going to use and how you do it. Questions about that? All right, let me switch back over to this. Okay, so that's a good example of using the M1V1, M2V2, just making a dilution and describing the solution preparation, both of those. You in the real world, you have to make a whole lot of solutions. All right, gas collected over water. Number 9. So this is what we did. It didn't look exactly like this. We did not use a eudiometer, which is a gas collection tube. We used an inverted graduated cylinder. Y'all remember? We filled it with water and then tipped it up, held it upside down in the bucket of water, and then collected the butane into the graduated cylinder to displace all the water. Y'all remember?
Oh yeah.
Yeah, so that's one. The
Wasn't
way we
that-
did, yeah.
Wasn't that with the lighters that were like kind of broken?
Yeah, we used up all the rest of the butane in some of those lighters. And so we just collected the butane. We collected a known volume at a known pressure. The pressure is the atmospheric pressure of the day. And then we figured out how many moles of gas that was and what the molar mass was. We did that. So here's another way that experiment could look if you had a reaction going on. This is one I always do the last week of school. And I hate that we didn't get to do it this year. This is where we melt potassium chlorate and make oxygen gas. But instead of collecting the gas, I like to feed gummy bears to the oxygen gas. And we call it like sacrificing gummy bears to the fire gods. So
Didn't we do a little bit of that in Chem 1, or is that something
for
different?
sure. I do it at the end of every semester, usually. So yeah,
That's
you
what I
remember
thought.
doing that. You melt potassium chlorate and it decomposes. It does this reaction right here. Decomposes into potassium chloride and oxygen. And if you have it in a test tube like this, the standing up, the oxygen just sits in that tube. And if you drop sugar into your pure oxygen, into your molten potassium chlorate / pure oxygen, it reacts very, very, very quickly. It's a very exothermic. It's basically rocket fuel. You shoot flames and gas out the end of the test tube. Those test tubes are done for. We don't even try to clean them. It's fantastic. I love doing it. One of many things that we didn't get to do this semester. Dang it. But if we didn't ignite our oxygen, we could collect it through water, and it would be like this. Any number of reactions that produce a gas, a good way to collect that gas so that you're not losing it is by bubbling it through water. But do y'all remember what we had to do? We had to get the temperature of the water bath because you're not just going to collect the gas you intend to, you're also going to collect some water vapor. And the amount of water vapor you collect depends on the temperature, and that's it. It only depends on the temperature. You don't want to use warm water because gases are not, room temperature is best, basically. So, I mean, gases are more soluble at warm temperature. You don't want warm or super cold, really. Okay, so this is about reading the volume of the eudiometer. We didn't use a eudiometer. We used the graduated cylinder, but the exact same idea where we had to get the level of liquid inside the graduated cylinder exactly level with the water in your water bath. And then we had to find out what that pressure of the water vapor is. This is from a chart. if you need this information, they will give it to you. It'll be a chart that shows you the water vapor pressure at certain temperatures. So I remember what ours was. It was, I think it was like 21.4 torr. It's a small amount of torr compared to the atmospheric the pressure of the gas. Oops, let me let my dog in. He's barking. Sorry, I'm back. So the pressure of the gas would be exactly equal to whatever the atmospheric pressure of the day is, which we looked up on the weather app, except you have to subtract out this tiny bit of water vapor pressure. So pressure of gas equals pressure of atmosphere minus the pressure of the water vapor. You remember doing that?
Yeah.
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 All right. And then next one, the percent composition of the hydrates. That's the last one. This is a lab that everybody should have done in Chem 1, where you have, we always use the copper sulfate hexahydrate. It's blue. You put it in the crucible, and then when you heat it, it turns white. Y'all remember doing that lab?
Yes.
I think so.
So you heat it, it
Something
turns
like that.
white. So a hydrate is just any salt that crystallizes with molecules of water attached to it. And so let me show you what this one looks like. So that one that we used before was copper sulfate, heptahydrate. And so the formulas look like this. Y'all remember seeing this? Where you have a little dot and then some water molecules attached to it. So the name of this one is really copper 2 sulfate heptahydrate. And if you're adding up the molar mass of a hydrate, you add in those 7 molecules of water. You add it all up. But when you heat this, it turns into the totally white, not so exciting copper sulfate anhydrous. You call it, when the water is gone, we call it anhydrous, without water. And so, mass of the hydrate, you heat it until the water is gone, cool it and weigh it, heat it again, cool it and weigh it. If you have a constant mass, you're done. And the difference between what it weighed when it was blue and wet here versus the mass that you get at the end when it's all the way dry and white, that tells you how, if you don't know the formula, supposedly. And so that tells you how many grams of water were lost. You can change that into moles of water that were lost, and then figure out how many moles of water for every 1 mole of copper sulfate, or whatever the hydrate is. Most common mistake is not heating it enough, or weighing it while it's hot. You cannot get the mass of a crucible while it's hot. You can't get the mass of anything while it's still warm. The balance is all over the place. So our lab was called empirical formula of a hydrate. You could just as easily do it as a percent composition, like figure out the percent water that's in there. Percent water, if they asked you for percent water, you'd want it's always part over the whole times 100. So grams of water over total grams of sample times 100. And here's the example that we just talked through. The blue crystals. And then when you heat it, it turns white. The cool thing is, if you add water to the white powder, it turns back blue again. Y'all remember doing that in first year chemistry?
I don't think I did that.
If you put a few drops of water into the white powder, it like sizzles and turns blue again.
I remember doing that.
I love it. It's one of my favorites. All right, and then y'all's last page is the glassware. Except Oh, and how to read the meniscus, how to read the volume. No matter what you're reading, instrument-wise, make sure you estimate one additional digit. So if it has marks for every milliliter, then, or for every 0.2 milliliters, 0.1 milliliters, whatever it is, you read all the marks that are there and then one additional place. And you read it from the low part, the bottom of the meniscus, right? All right. That is what I wanted to go through with y'all today, the lab stuff. Getting dark on me out here. What do you guys, I mean, seriously, if y'all want to work review questions and you just want to send me questions or whatever, I will, I'll probably answer you any time of day or night. So feel free to do that. And then, yeah, and if anybody wants to do more review tomorrow morning, I'm up for it.
I'll be up early tomorrow, so I'd be okay with that.
Miss Hatchett has us having a Zoom call at 9 a.m. for review for the AP Psych exam.
What?
Yep.
But if I can get like out of that earlier, yeah, she sent a reminder about it like 2 days ago or yesterday or something like that.
I did not get that.
Aiden is
Yeah,
like,
it's
what?
9 a.m. It's a Zoom call. I'll send you the link.
Y'all don't need to be zooming on AP Chemistry Day about psychology.
Yeah, I know, and like
Yeah, no,
I'm more worried about this because AP Psych I can search all the answers, so I'm not worried about it.
AP Psych is gonna be a breeze.
When is that
This-
test?
Next Tuesday, I believe.
Oh wow, you got plenty of time then.
Oh yeah, exactly. And like I'm just confused. I was like, I should ask her if she could remove it, but then I was like, it's only 3 of us in AP Chem.
Well, what time do y'all want to meet tomorrow and go through some more stuff? I don't need to.
I would
I'm
love to
okay with that.
personally.